I just revolved around the y-axis. Hey, we're gonna sum stuff up. I hope you just said, what stuff? Exactly, we gotta figure out what stuff we're gonna sum up so we can figure out how that integral is gonna go. Need my marker. So in this case, we're gonna take the function sine of x. Do you see the famous sine wave? But only on the interval from 0 to pi. And we're gonna take that region underneath that curve bound by the x-axis, and we're gonna revolve that little round of mound of region, if you will. But we're gonna revolve it around the y-axis this time. And we would like, again, to find the volume of the solid formed when that sine of x graph is revolved around the y-axis. So let's get to work. First of all, if we were to take that region and slice it up, as we like to do, into infinitesimally thin, infinitely many pieces, what would a slice look like? What stuff are we going to sum up? So I've tried my best to draw it here. Can you imagine here in red? Imagine a slice right here. Remember, we're revolving around the y-axis. And so what we produce here is a cylinder that would be about yay tall, would look about like this. So can you imagine finding the volume of this cylinder? Now what's important to note here is this cylinder, you know what's inside of it? Nothing. This is not a full solid cylinder. This is a outer shell of a cylinder. It's like just the wrapper on the can. It is not a solid cylinder. So we have to think about how would we find the volume of just the wrapper on the can of just this cylindrical shell. Can you imagine another slice? And I'm just showing you a few. Remember, there's infinitely many, so I can't show you them all, but I want to show you one more here in green. Can you imagine a slice right here revolved around the y-axis? It would produce a cylinder about like this. So can you imagine finding the volume of this cylinder? Once again, what's inside of this cylinder? Nothing. It's just the outer shell of the cylinder. It's like the wrapper on the aluminum soup can. Or can you imagine this one out here in orange? I didn't draw it because it's a little weird. It's like this. Ooh. Can you imagine the cylinder out here? It would look something like this. A relatively short, compared to the other ones, cylinder, but again, just the shell of the cylinder. So what we need to do is, if you can imagine this, find the volume of this piece of paper. Find the volume of this piece of paper. Find the volume of this piece of paper. And actually there's infinitely many more of them in here. And if we could find the volumes of each and every one of those infinitely many, infinitesimally thin cylindrical shells and sum them up, we would have the volume of that mound created. So what would a single cylindrical shell's volume look like? I tried to draw it here, but here's the point. Take your cylindrical shell, the wrapper on the can, if you will, and take the wrapper off. What used to be a cylinder is now a rectangular solid. Now I say it's a rectangular solid. It has a length, it has a height, and theoretically it has a little bit of width. Now even this piece of paper has a very thin width. In calculus, it's even thinner than what you see here. The width of this piece of paper in calculus thinking is infinitesimally thin. So what we have here is a volume of a piece of paper, the cylindrical shell. Well, we know that the volume of a rectangular solid like this is length times width times height. But let's talk more about what this volume would look like in the context of one of these cylindrical shells. Let's start with the length. Before the length was the length, when this thing was a cylindrical shell, you see, let me show you this one. The length was actually the circumference of that circle. So the length of the cylindrical shell corresponds to the circumference of the circular base. So this length is going to be found by taking 2 pi times the radius, formula for the circumference of a circle. The height. Now the height of the shell, notice the height of this blue one, the height of this red one, even the height of this orange one, the height is going to vary depending on x between 0 and pi. The height is going to vary. It's going to follow the sine of x function. To get the height here, we would input this particular value for x, find the sine of x, and output the height. To get the height of this particular cylindrical shell, we would input the appropriate value for x, find the sine of x, and output the appropriate height. Same thing here. So the height is going to correspond to the function that we're dealing with, in this case, that sine of x function. And then the width of our shell is the little infinitesimal change in x that we're speaking of. So the width is going to be that delta x. So the volumes that we're talking about are the lengths, which are going to be 2 pi times r, the width, which is going to be a change in x, and the height, which is going to be some function value. That height's going to change depending on x. And notice I just rearranged it to put the dx on the end because we like to do that. That would be the volume. And as we like to do, if we sum up all of those 2 pi r's times f of x times dx. Let me just change colors a little bit here. Remember, this is our radius. And remember, this is our function value, or our height. Let's just figure out what should go in each of those spots. And we're going to sum those up from 0 to pi, because that's the interval that we're focused on. Everything is going to be contained as we revolve between 0 and pi. All right, let's talk radius. Now, to just kind of see it in living color here, the radius of this inner red shell would be that. Or the radius of this little bit larger would be that. Or even this orange one, which I haven't drawn in, but I hope you see, the radius would be that distance. The radius is a distance from the x equals 0 to whatever value for x, to whatever value for x, to whatever value for x. The radius is just whatever x value we're dealing with between 0 and pi. See, when x is 0, there's a hypothetical or theoretical shell that has a radius of 0. And then when x is 0.2, there's a radius of 0.2. When x is 0.4, there's a radius of 0.4, etc., 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 until when x equals pi, we have that theoretical shell of radius pi. So the radius just varies from 0 to pi as x varies. And then, of course, our height, I've already mentioned. The height just follows that f of x function depending on which shell we're talking about. Oops. We know that f of x in our case is the sine of x. So if we integrate this, we will find the volume of that thing right there. Now remember, what we're really doing is we're summing up the volume of this cylindrical shell plus this cylindrical shell plus this cylindrical shell, except instead of just 3, there's infinitely many of them to get the volume of this mound that we're talking about. All right, let's do it. I am going to encourage you right now to pause this video and try this integral. And you know what? Just for fun, just do it by hand. Yeah, you can go on Wolfram Alpha and check it later, or Desmos and check it later, but just for fun. It is fun, isn't it? Just try integrating it by hand and then come back and we'll see how you did. All right, here I go. I'm just going to keep it going over here for now. So I like to pull the constant of 2 pi out front, and let's just integrate x sine of x from 0 to pi. Now, x sine of x, you can look for some structure. You can see like the x is not the derivative of x because the derivative of x is 1. And you can know there's no u substitutions. It's none of that stuff. What actually is happening here is a beautiful, perfect integration by parts. We have a u dv going on. And so we should integrate this thing by parts. And hey, we all know, let's be honest, that if integration by parts is part of the game, we kind of like the tabular or the tic-tac-toe method, as Jaime Escalante would call it. So x, differentiate x. The derivative of x is 1, the derivative of 1 is 0. Anti-differentiate sine of x. The antiderivative of sine is negative cosine. Because the derivative of cosine is negative sine, and so we need a negative cosine here. And then the antiderivative of negative cosine would be negative sine. And then remember, all Jaime Escalante, it's plus, minus, plus, etc. So this times a positive, this times a negative, and so this integral will be 2 pi times x times negative cosine of x times a positive, so negative x cosine x. And then 1 times sin x times a minus, so minus 1 times sine x is just sine x. And then we're going to evaluate this thing from 0 to pi. I'll come up over here and finish it off. So what we now have is 2 pi times, let's do the fundamental theorem, negative pi cosine of pi minus the sine of pi minus, plug in a 0. Now, 0 times the cosine of 0 is just going to produce a 0, minus the sine of 0. The sine of 0 is 0, and so all that's just going to be 0. So what we have is 2 pi times, let's see here, negative pi times the cosine of pi. Now remember, cosine is that horizontal leg on the right triangle on a unit circle. So if you went over to pi, that horizontal leg would be a negative 1. And then the sine of pi is 0. And so we have 2 pi times pi. We have 2 pi squared cubic units is the volume of that object formed when the sine of x from 0 to pi is revolved around the y-axis.